Good morning, everyone. Thank you for being here. Today, I will be presenting my MSc dissertation project, Chapter 1 and Chapter 2, which is titled Data Augmentation for Phenome Based Lip Reading, a study aimed at improving silent speech recognition or SSR through customized data augmentation strategies. To begin, let's quickly look at what lip reading really is. Lip reading, also called visual speech recognition, is the process of interpreting speech based solely on visual cues, mainly lip, tongue, and jaw movement, without relying on audio. The technology is incredibly valuable in noisy environments for people with hearing loss or in silent video applications such as surveillance or archival restoration. A key subfield of this area is phoneme-based lip reading, which try to decode individual phonemes, the smallest unit of sound in speech, rather than full words or sentences. With this provide greater accuracy in ambiguous cases, it comes with unique set of challenges. Moving on towards the next slide, key challenges. Now let's explore the core challenges faced in phoneme-based silent speech recognition. First, we have visual ambiguity, often caused by the visemic overlap. For instance, phonemes like P, B, M have very similar lip movements and are often indistinguishable without sound. Second, speaker variability is a major hurdle. Each person speaks differentiately. Factors like lip shape, facial structure, accent, and even head movement can introduce inconsistency that confuse the model. And third, we face a lack of device phenome label dataset. Most available datasets are focused on sentence level and word level transcription, and they often lack phenome level granularity. These issues combined significantly limit how well a model can generalize to unseen speaker and real-world scenarios. Moving further towards the next slide. Here we will discuss the proposed data augmentation. To tackle these challenges, I have developed a custom data augmentation framework that focuses specifically on film level modeling. Unlike general image augmentation technique, which might distort important speech cues, this framework is designed to preserve the integrity of phenome articulation. Some of the technique I have used in my research area are temporal warping to stimulate faster and slower speaking style by reading different papers, Vizim preserving noise injection will introduce visual variability, synthetic frame generation, which helps simulate rare phenome transitions, and lip sync misalignment, which mimics real world imperfections like poor frame to phenome synchronization. Together, these techniques create more device training data while keeping the visual phenotypic cues intact. These improve model robustness to ambiguity, lightning change, and speaker diversity. Moving further towards the next slide. Here we will discuss the evaluation metrics. To evaluate performance, I use three key metrics, each telling a different part of the story. Word error rate help us understand how well the model reconstruct entire sentences from the predictive phenomes. Second one is character error rate, provides more fine-grained insight, especially useful for assessing phenome to character conversion accuracy. And finally, BLEU score, which is also known as blue score, which is commonly used in machine translation, help measure the linguistic quality of the output, how closely it resembles real spoken language. The results showed that the models trained with augmentation framework consistently outperformed baseline model in all three metrics. What's more, the improvement were particularly noticeable in challenging scenarios like how lightning, blur, and when tested on new unseen speaker, this will prove that the targeting augmentation significantly increase the generalizability. Moving further towards the next slide. Here we will discuss model architecture. So in terms of architecture, I trained and evaluated two types of deep learning models, and I have researched about them. I have researched about two models, and in the starting phase, I have like going to train the first model. First was the by LSTM, Long short-term memory model trained using the connectionist temporal classification laws or CTC. This is particularly good for sequential data where alignment is not always clear. Second, I will train is that transformer-based model which excels in sequence-to-sequence learning, especially for converting phenom predictions into readable text. I trained both models on LRS2 dataset, which is ideal for phenom-based research due to its detailed annotations and speaker diversity. The overall pipeline began with video preprocessing, extracting frames, aligning with the new frames, phenoms, and then running data augmentation before feeding the data into the models. This modular yet integrated approach allowed me to experiment with data augmentation both before and during the training. Moving further towards the last slide, here we will discuss the research contribution and the future direction. So, what's the bigger picture here? This project contributes methodologically and practically to the field of silent speech recognition. On the technical side, it introduced phenom-aware augmentation method that can easily be integrated into the existing lip reading pipelines. On the practical side, it improved the real-world applicability of SSR models, especially in assistive technologies for hearing impaired, silent command interfaces for variables, and restoration of historical footage. For the future, I would like to extend this work by incorporating multimodal data such as head movement, facial expression, and even residual audio features. I also believe there is a great potential in applying the large language models to improve phenomenon-to-text translation, provided we manage input noise effectively. And finally, addressing bias and fairness, such as ensuring demographic diversity in dataset, remains an ongoing challenge. So I plan to explore further. Overall, this research has shown that with the further right augmentation techniques, we can make a lip reading technology smarter, more inclusive, and ready for the complex real-world use cases. Thank you for your time. I will be happy to discuss any part of the methodology further.